Today's tutorial is about vertical motion. Vertical motion is the motion we exhibit as something is falling down. If I release this marker and I let it drop, that would be vertical motion. It's going in the up and down, and sometimes we refer to this as in the Y direction. The first thing that we need to look at is at free fall. Free fall is any force acting on an object in its downward due to the force of gravity. Gravity is constantly pulling it down, and that's the only thing that we're looking at. It's not taking into consideration any resistance that we would feel as an object goes down, such as air. Along with this free fall, you need to consider the acceleration that is occurring. It is constant acceleration, and it's constantly at negative 9.8 meters per second squared. Again, note the negative is because it is in the downward direction. Initial velocity of any free-falling object, it would be 0. Now, we can eventually throw something down, so we would have to account for that velocity. But on the onset, as we're looking at these free-falling objects that are just coming down on their own, we would say that initial velocity is 0 meters per second. The distance between seconds as an object falls increases. It's not constant distance. It's not a straight line the way we would see it on a graph where it's equal intervals every time. It increases that interval as something is going down. The velocity of the object is also increasing. So as something is falling down, each second the velocity has increased by that much more. And we'll look at the equation in a second so you can understand how this is happening. But along with this increase of velocity, eventually an object may hit what we call terminal velocity. It is still falling down. It is still moving extremely high velocity, but it no longer increases in velocity. Its velocity is now constant. You're kind of on cruise control on the way down. Extremely fast cruise control. Please keep that in mind. And I kind of drew a little picture here of how this would occur. As gravity is pulling down, air resistance is pushing up. If we're talking about air resistance, that's the only way we would hit this terminal velocity. And so someone with a parachute would be able to actually hit that terminal velocity, because as this force going downward equals the force coming up, it kind of stabilizes, so it allows it to quote-unquote float down, and it's now a little bit more under control. Like I said, it is extremely fast moving, but it is a little bit more controlled. Now, I've put over here, in essence, the equation that we would be looking at to figure out the distance of the fall. If we know, and I put y because we're talking about, the up and down vertical direction, and we can look at it in terms of the y-axis versus the x-axis. Anyway, we have dy equals v naught multiplied by t plus 1/2 times acceleration due to gravity multiplied by t squared. It's the same equation we were looking at as we were talking about horizontal motion, but now we're changing the direction. Now, final velocity can be calculated if we have time by looking at final velocity is equal to initial velocity plus acceleration due to gravity multiplied by time. Again, we know that initial velocity is 0, so we can actually simplify it by saying Vf is equal to AGT. Here we have someone that is taking a little nice dive off a cliff, and at t0, in other words, 0 seconds, obviously the velocity is at 0 and the distance is 0. Not yet coming down. Now remember, it's almost like at the very top, you're suspended there and then you start moving. Well, after the first second, we have velocity at 9.8 meters per second, and the distance traveled downward has been 9.8. Second, we see an increase in velocity. Now you're going 19.6 meters per second, and your distance happens to be 19 meters. But watch, interestingly enough, at t3, our final velocity, or our velocity at this point, is 29.4 meters per second. But look at what happened to our distance. We're at 44.1 meters per second. Quite a difference between one to the other. At T4, our velocity is now increased to 39.2 meters per second, and our distance has gone up to 78.4. So you see that the distance falling is now bigger and bigger as we go. The last one here, or second to the last one I wrote, is at t equals 5 seconds, our velocity is 49.0 meters per second, and our distance is 122.5 meters. And the very last one that I wrote down here at the very bottom is T6. Velocity at that point would be 58.8 meters per second, and our distance would be 176.4 meters. So let me fix that really quick because I guess I wrote mine wrong. There we go. 58.8 meters per second. That's 6 seconds after coming down, after you have started to descend. So it really increases by a lot. That's a very hard hit. If you're going at that velocity, when you hit something, that's going to hurt. Hence why falling down hurts. But this is a very short idea of what vertical motion would look like.